Hello and welcome. Differentiation under the integral sign. Do is. The integral we have to do today is e to the minus x minus e to the minus 7x, the whole thing over x sec x. And the same integral, of course, you might see it exactly the same, of course, right the sec on the top as a cos. I think I was just looking at my book and I have, after this integral, I have exactly the same but with the cos, and just different, of course, powers on the exponents. And this is the first, I did remember today to actually check the answer that we ought to get for this. I never do remember it. This should be equal to log 5, so we have something to check our answer at the very end. Okay, so we've done a few of these today, not today, in recent times, so I'm going to speed up a little bit, I think, today. So I'm going to call this integral I of something. I'm going to put, I'm going to fill that argument in a minute, and I'm going to define the integral. I said I'm going to define the integral and define nothing. So not a very good start to this lecture. We're going to introduce a parameter, and a sensible place to introduce a parameter is on one of the two exponentials. So we can either say e to the minus kx or e to the minus kx instead of the 7. In fact, we can actually do this integral by putting two parameters, let's say alpha and beta, and get a general expression that will work for any powers that they might give us. So we'll have a general result. But today we're going to do it for those two quantities. Okay, so let's call it the parameter k. And I'm going to put the k instead of the 7. The rest, of course, exactly the same. So my I of k is the integral not to infinity, e to the minus x minus e to the minus kx over x sec of x dx. So, of course, if I define this as my I of k, the one that I'm trying to find is going to be simply my I of 7. In other words, putting k is equal to 7 should give me my answer. Okay, we're going to start with the standard routine. We're going to differentiate this line with respect to k. di by dk is equal to, let's put the extra line. I was going to move it straight inside the integral, but it's best for us to actually record it first of all. Is d by dk of this integral here. I'm leaving some space so I can just rub it off in a second. E to the minus x minus e to the minus kx over x sec of x dx. And of course, by Leibniz integral rule, I can move now this, because I've got constant limits, I can move that inside. Strictly speaking, I should really write it as a partial derivative now, because of course the integrand has, of course, k's and x's. So I've lost it from the front. So I swapped integration and differentiation. Now, because I'm going to be speeding up a little bit today, I don't want to put extra lines, but picture this for a second. If I split this integral, or no, this integrand rather, into two bits, e to the minus x over x sec x, and I differentiate that with respect to k, is goodbye, my friend. There's no k's in there at all. Therefore, that will produce nothing. And the only thing, that's what I'm doing at the moment, when I'm carrying out my differentiation with respect to k, I'm looking at this term here, of course, including the minus at the front. So if I differentiate this with respect to k, a minus x will come to the front, times a minus will give me plus x e to the minus kx, and of course over x sec x dx. And of course the whole point of that is to lose this x, okay, because that has gone. And if you're not happy, you cannot quite see what I've just done in there to go from this line to this line, please split that into two separate quantities, split your fraction, and then carry out two separate differentiations. Okay, you know how I feel about this particular integral that's coming up. E to the minus kx times cos x. This integral or sign there, it doesn't really matter. I hate it with a passion. I really do dislike it. Annoyingly, here it comes to haunt me again. I'm going to do it with complex numbers. I'll try to use different methods to actually show you how to do this particular one. So this is equal to, I'm going to say that's the real part of not to infinity e to the minus kx, and the cos, of course, is e to the ix. The real part of that, of course, it'll be the cos of x, which I'm seeing in there, dx. Compact now your integrand. So we got real part integral not to infinity, and this I can write as e. I'll put the x as a common factor, so I'm going to have a minus k plus I, lots of x on the exponent, dx. Carry out, I lost, no, I didn't lose anything, sorry, I beg your pardon. I'm going to integrate that now, still real part of 1 over minus k plus I, that's the constant of the exponential, e to the minus k plus I lots of x, and this bracket that I'm putting at the moment is going to double up as for the real part, the real part argument, as well as the evaluation bracket, because I don't want to write another bracket there. Okay, what do we have now on this particular line? First of all, let me conjugate this. So this is going to be still real part, and if I conjugate that, it's going to be minus k minus I over k squared plus 1. Let's go back into the usual form for this. So it's going to be e to the minus kx, that's that bit there, times an e to the ix, still to be evaluated between the limits of 0 and infinity, and then take real part. I'm going to put the limits first of all, and the limits, when I put x is equal to infinity into this quantity here, these are irrelevant, these are finite and constants. This, the k being positive and having a minus in there, it will go to 0. So I'm going to have real part of 0, that's by putting the infinity for my x in here. Of course I'll put it here, but that's finite, okay? You can write in sines and cosines if you're unhappy about what I'm doing in there. This term here will just kill it. And when I put x is equal to 0, 0 here and 0 here, these are both 1s. So the only thing that's going to survive is this quantity at the front minus that quantity. And because I got two minuses there, let me write as a plus and put k plus I over k squared plus 1. And of course the real part of that is k over k squared plus 1. Okay, so I managed to actually find so far, let's clear the board, not my integral, I haven't found my I of k, I have found my di by dk, and this turned out to be, let's clear the board and write that on the very top. Let's write it before we lose it. That is actually k over k squared plus 1. This will be a very easy and straightforward integration to do after this. So, integrating now both sides of this equation with respect to k, I'm going to get my I of k. And let's also write what I of k is as well, apart from the integration I'm going to do in a second. My I of k is, of course, 0 to infinity, e to the minus x minus e to the minus kx over x sec x dx. And carrying out this integration, this is quite silly, is of course a half log of k squared plus 1. It doesn't need mods, and of course the constant of the integration. Okay, so at the moment I just need to find what this constant is, and I'm done basically. And finally, once I get my I of k, put 7 in there, and hopefully I get my log 5, which it should be my answer. So what value shall I substitute for my k in here in order to evaluate this particular constant c? I'm just looking at the integrand here, and this quantity here. It'd be lovely if that was a 1, of course, because if that was a 1, e to the minus x minus e to the minus x is kaput, 0. So I'm going to say, okay, let k is equal to 0. All of this integrand will become 0 as a result, and therefore the whole integral will be 0. So 0 will be equal to, I'm putting k is equal to 1 here. I'm going to get a half log 2 plus a constant. So my constant is in fact negative half log 2. I don't want to be just rewriting it again. I'm just going to write it here. My constant c is minus a half log 2. And can I write it perhaps a little bit better? or can I just evaluate it? I can't just go ahead and evaluate it, put k is equal to 7, finish it off. It doesn't matter. Yeah, probably I will evaluate it. So my I of 7, which of course is the integral that I'm trying to find, is going to be equal to, as a result of this result, a half log 7 squared plus 1 is log 50 minus a half log 2, and factorize the a half will give you, of course, the log of 50 minus the log of 2, which is log 25, which of course, it doesn't matter how you see it, that is going to be, of course, the log of 5, elementary A-level maths, which is, of course, the answer that we got in there. I hope we are getting better at this. I hope you're following what's going on. The partial differentiation, not that difficult as you can see. It's quite straightforward once you've done a few of these. I hope you join in very, very soon. Who's laughing now?